Now, the first topic that we have to cover is topic number one is about is 5.1 in part A is about forces forces in uniform electric and gravitational field. Yet there are some questions about non-uniform fields. However, the topic is about forces in a uniform gravitational or electric field. So first of all, we must say, we must understand that in a gravitational force, in a gravitational field, the in a gravitational field, the gravitational force is always attractive. It can never be repulsive. The gravitational force is always attractive. And one more thing, gravitational force, gravitational force is always gravitational force is always in the direction is always in the direction of the gravitational field. It's never in the opposite direction. So one thing that you must know is that if this is a uniform gravitational field, the field lines represent, their arrowhead represents the direction of the gravitational force on a 1 kg mass, and the uniform spacing here shows that the field is uniform. Let's suppose this is a uniform gravitational field. Now, you can think about it that the gravitational field must be vertical. So I should clear that in a 3D space, there is no horizontal or vertical. When you take the Earth, the gravitational field lines are perpendicular to the surface of the Earth. However, when you take a small region on the surface of the Earth, in a small region, the gravitational field is uniform. While in the large region, it's never uniform, and gravitational field lines are perpendicular to the surface of the Earth. Just for example, if you only take a small region on the surface of the Earth, just for example, if you only take this region, this much region, then the gravitational field lines would be, if you zoom in, then these lines here, they will be, for example, the lines here will be uniform. So over a small region on the Earth, the gravitational field will appear to be uniform, while when you take the whole Earth, it's not uniform. So it depends on what you are taking. If you're taking a small region on the surface of the Earth, then the gravitational field is taken to be uniform. However, if you're taking a large region on the Earth, then the gravitational field is not uniform. So in the questions that we solve in A2, we assume the gravitational field to be non-uniform. While in A1, our problems are based on small regions above the surface of the Earth. That's why the gravitational field lines are assumed to be equally spaced and the gravitational field is assumed to be uniform. In our real life, the distances are small, 100 meter, 1000 meter, 500 meter. So we have small distances. For these small distances, our daily life distances are small, or our daily life heights are small, because of which we assume the gravitational field in our A1 to be uniform. So in A1 problems where we have daily life situations, the gravitational field is assumed to be so in our daily life problems, we assume the gravitational field of the Earth to be uniform. However, in our A2 problems, when we deal with satellites, meteorites, or the objects which travel through large heights in excess of thousands of kilometers, then we take long distances, and there we take the gravitational field of the Earth to be non-uniform. So one thing should be clear: when we take this much region on the surface of the Earth, we can take the gravitational field of the Earth to be uniform. However, if you take 2 points like X to Y, this much distance, then the gravitational field of the Earth will not be uniform. So the gravitational field of the Earth could be uniform or it could not be uniform, depending on the problem consists of how much region, what region you are covering. If the problem is over a small region or over a small height, then the gravitational field of the Earth may be taken to be uniform. If the region is long or the height is long, then you cannot take it to be uniform. So we must write that gravitational field of the Earth is uniform for small or short distances or heights. So when you are dealing with small distances or heights, the gravitational field of the Earth can be taken to be uniform. However, for long distances, when you take long distances or heights, for example, as you take from X to Y, for long distances or heights, gravitational field of the Earth is non-uniform. So the first thing we are doing is the first thing that we are discussing, this is in A1 syllabus. In A1 syllabus, we solve daily life problems and we assume the gravitational field of the Earth to be uniform. And this part is for A2. In A2, we are solving problems over long distances where the gravitational field of the Earth is like you will take it to be non-uniform. Now, in our understanding, we are assuming a uniform gravitational field. And one thing, in 3D space, there is no horizontal or vertical. If you draw the lines horizontally, vertically, whatever, it will not matter. The important thing here is the lines are uniform. And if you call it a uniform gravitational field, you can also draw it vertically, it will not matter. The lines could be drawn in any direction. One important thing is the lines are uniform. The uniform lines show that the gravitational field is uniform. Whenever you have a uniform gravitational field, its lines will be uniformly spaced and the force on a mass will be, as you see, if this is the mass, then gravitational force on the mass will be in the direction of the gravitational field. And this force is generally called the mass of the object, sorry, the weight of the object. Here, the gravitational force will be this one. So one understanding is here is if field lines, if field lines have a uniform, if field lines have a uniform spacing, if field lines have a uniform spacing, then the gravitational field is uniform. This is the first thing. And the second thing is gravitational force, gravitational force or weight, gravitational force or weight is always in the direction of the field lines. Now the topic is only about the uniform gravitational field lines. However, some problems also deal with non-uniform gravitational fields. So for example, if you have a gravitational field which is becoming stronger, if the lines are getting closer, then the field is becoming stronger. And let's suppose the field is directed towards right hand side. So the field is towards right and the field is getting stronger. We can say that it's a strong region of field and this is the weak region of field. So the spacing, here you see it's more spacing. More spacing represents more spacing between the field lines. More spacing between the field lines represents a weaker gravitational field. And here you see it's less spacing between field lines. It shows a stronger gravitational field. Less spacing between field lines shows a stronger field. So the field strength is basically about the density of the field lines or population of the field lines. If the field lines are more populated or more dense, it represents a stronger field and hence more force. Now let's suppose you have a mass m here. What will be the force on this mass? If the gravitational field lines are curved and they are not straight line, then the force is tangent to the lines. If you draw a tangent here, this tangent in the direction of the field will represent the gravitational force. For example, if you want to see force at this point, for example, this point was point P, and now you keep a mass at point Q, for example, then you need to draw a tangent again, and this tangent will represent the gravitational force. However, if you have a mass here at this point, for example, this point is point R, here the gravitational force will be along the field line. So the field lines are inward. It depends wherever you are. If the line is straight, then the force is along the line. If the line is curved, then the force is tangent to the line. However, the gravitational force is always in the direction of the gravitational field. Now the concept of electric force, the concept of electric force in an electric field. So initially we'll deal with a uniform electric field. For example, if you have two parallel plates, the field between the parallel plates is uniform. You'll get uniformly spaced lines which represent a uniform, which represent a uniform electric field. And electric field lines are always directed from positive towards negative. And electric field lines, what they represent? Electric field lines represent two things. Electric field lines represent two things. basically two things are there which are represented by the electric field lines, and you must know that. The first thing that they represent is the direction of the electric field lines, that is the arrowhead basically. The direction of the electric field lines represents the direction of electric force on plus 1 coulomb charge. So the direction of the electric field lines represents the direction of electric force on plus 1 coulomb charge. And the second thing that they represent is the density or population, or you can call that spacing between field lines. So density or population of field lines represent the magnitude of electric force. So these are the two things that you must know. And one thing that is important is that you must know that electric force on a positive charge, if you get a positive charge like a proton, alpha particle, or a cat ion, electric force on a positive charge is always in the direction of the electric field. Electric force on a positive charge is always in the direction of the electric field, while electric force on a negative charge is always against the electric field. So electric force on a positive charge and electric force on a negative charge. Electric force on a positive charge is always in the direction of electric field, while electric force on a negative charge is always against the electric field. Let's suppose if you have this electric field, if this is an, let's suppose this is an electric field, and we take a positive charge here, and the force on the positive charge is in the direction of the electric field, and if we take a negative charge here, the force on the negative charge is against the electric field. So this is electric field. However, the electric field could be horizontal, vertical, or in any direction. You may have an electric field that is vertically downwards, Electric field is always directed from high potential to low potential. For example, this field represents that the left-hand side would have been a high potential. The left-hand side would have been a high potential, while the right-hand side will have been a low potential. So electric field is always vectored from the high energy state or the high volts towards the low volts. So this field represents that here you have high volts and the bottom point is at low volts. Now, if you get a positive charge here and a negative charge here, force on the positive charge will be in the direction of the field and force on the negative charge will be opposite to the field. So this is the concept of force on a positive charge and a negative charge in electric field. What if the field is non-uniform? Although it is like here we only have uniform fields, but there are some problems about non-uniform fields as well. So we must understand the concept of electric force in non-uniform fields. What if the field is non-uniform? Just for example, if we have this field here, no, it's the same principle. If the spacing between the lines is increasing, the field is getting weaker. Now let's suppose these field lines are towards left, which shows that this side was at, here we have high volts, and here we have low volts. It is the value of potential or volts that determines the direction of the field. The field is always from high potential to low potential, and here the field is non-uniform. Now let's suppose here you have, this is point X, and point X is position of a positive charge. Now if point X is the position of a positive charge, then force on the positive charge is in the direction of field. Yet one thing that you need to understand is that if the field is curved, then the force will be tangent to the field. Here you need to draw a tangent. This tangent represents the force on the positive charge. Now for example, if you get another situation where the charge is negative, let's suppose Y is the position of negative charge, then force on the negative charge, as you know, is opposite to the electric field, yet the force will be tangent to the field. Yet the force will be tangent to the field if the field is curved. So if the field line is curved and not straight, then the force is tangent to the line. Here we have a weak field because the lines have more spacing, and here we have a strong field. Now for example, if you get a negative charge here, then the force will have a high magnitude, and this force will be opposite to the electric field. On the negative charge, the force is opposite to the electric field, while on the positive charge, C electron is negative, so the force is opposite to the field. Yet if the charge is positive, then the force is in the direction of the field. Here the field is towards left. Here the field is towards left. On the positive charges, the force is towards left. As you see here, and on the negative charges, it is towards right. Yet, if the field lines are straight, then the force is along the line. If the field lines are curved, then the force is tangent to the lines. Now, here we will, in this slide, we'll cover up to this point. In the next slide, we'll start from here on. Take care, students. Allah Hafiz.